Got it?
Maybe just
okay.
I'm
I will.
Yeah,
So
we can look at it tomorrow.
Him.
Oh, okay.
Okay.
Yeah.
Gotcha.
Sorry, I just have a lot going on.
Yeah, no, you're good there.
I'll start. Heavenly Father, we thank you for this day. I thank you for these students. Just pray you'd help us to use this time wisely as we prepare for math battle tomorrow, Lord. Amen. All right. Yeah, that's right. I have to come up with a math battle for you guys, isn't that right? Yeah. Let's see here. So you guys have questions? Yep.
If you have two functions that are being multiplied together, can you turn them both into series and multiply the series?
Yes, to find the series for a product of two functions, you know, it's not universally the case that you want to multiply the series. Like there are special exceptions to that. Like
If you have like x times 3
if I had like here, how about this one? E to the x times sine x. If I want to find the power series for that, say the Maclaurin series, the first three terms I would do, 1 plus x, 1/2 x squared like that, and multiply that by x minus 1/6 x cubed. And then, yeah, you just multiply like normal. That's x plus x squared plus 1/2 minus 1/6 x cubed, and so forth. Keep it order by order. And that's how you do it. Now, there are some exceptions. If there happens to be some there's like trick problems, So like, here's an example where you wouldn't want to do that. If I had sine x times cosine x, say times 2, I certainly wouldn't want to multiply the series to find the power series. I would want to go, that's sine of 2x, and then I'd go from there, right? So multiplying series here would be dumb. Just like if I had e to the x times e to the 3x, I wouldn't want to multiply the series. I would want to use algebra. I mean, it's not, but barring some trick, yes, multiply the series. Questions?
Can I do problem 259?
Which is, I don't have it in front of me.
Yeah, it's on. Sorry, it's on here. If you want to look at this.
This printed out funny. This is not Adobe, is it? Let's see here. The font's weird. Here you have, it has corrupted my typesetting. Beware of this printing.
That's Word's creation editor font, I believe. That's what's there.
Yeah, it doesn't look good. Anyway, x squared 3 to the x centered at 0, huh? So, all right, so this one is in some sense like a special case of what Josh was just asking about, because there's like x squared is a power series in some sense, but it's a stupid one. It's just one term, So really, all I have to do is find the Maclaurin series for 3 to the x. And the way to do that is to remember the relation to e to the x. So this is e to the natural log of 3 to the x. That's an identity, right? And so that allows me to convert to e to the log 3 times x, right? Or I like to write it x log 3 for some reason, but. And then that, yeah.
Wouldn't the x squared be 2 terms? That series?
You're thinking of the next problem, which is centered at 1, then the x squared has to be expanded.
It was centered at 1 with x.
This is 259. It's centered at 0. There's no need to expand the x squared. So then this would be, the sum n equals 0 to infinity, like natural log of 3 to the power n, x to the n, divided by n factorial. And then you just have to take that and multiply by x cubed, right? Is that clear enough?
Yeah, thank you.
Did you want to ask about 260?
I'm having trouble
No.
simplifying at the very end. You had said split split off the resultant series into its even and odd components.
Yeah.
I'm not entirely confident doing that yet.
All right, let me try something like 260, but not 260 itself. So let me call this 260 tilde, which is something like f of x equals to, is it x squared?
260 is f of x equals x squared 3 to the x, the same function centered at c equals 1.
All right, so I'll do times 2 to the x, haha, centered at c equals to 1. In fact, I'm going to make my life easier. I'm going to do e to the x. There you go. Having that 3 to the x just muddies it a little bit. But if we can understand this one, you can understand that one. So, and the intrinsic difficulty of rewriting the, let's see here. So, now that I see where we're going, I actually have another idea, but I'm not going to do it. All right, centered at 1. So that would mean x minus 1 plus 1 squared, and that's e to the x minus 1 plus 1. And so I just added 0. The reason I did that is upon multiplying, I get x minus 1 squared plus twice x minus 1 plus 1. And then over here, I get e times e to the x minus 1. And so what that's going to give me is e times x minus 1 squared plus 2 times x minus 1 plus 1 times the sum, n equals 0 to infinity, of x minus 1 to the power n divided by n factorial. Yeah.
I understand, also merging it, the two x minus 1.
Just multiply it out. Multiply it out. So this has the pattern. So what I'm thinking of is x minus 1 parentheses plus 1, right? Think of this like a and b. So if I square a and b, I get a squared plus 2ab plus b squared, right? So this is like my a squared, this is like my 2ab, this is my b squared. And that's my thought process there. But so then this is where it gets ugly a little bit. So f of x is, it's e times the sum, n equals 0 to infinity, of x minus 1 to the n plus 2 over n factorial, plus the sum n equals 0 to infinity of 2 over n factorial times x minus 1 to the n plus 1, right? Plus the sum n equals 0 to infinity of just x minus 1 to the n over n factorial. The question is, how would you combine those sums? And I might have said something about even or odd. I don't think that's actually constructive here because the exponential's got both even and odd. So I was really thinking more about something else. Maybe like that would have been a better comment if there was like sine or cosine here. So sorry about that. So I think, well, you can actually kind of see what's going on here. This one's, so this, if you look at this, think about this just conceptually. This is 1 plus x minus 1 plus stuff, right? So if you think about multiplying this by that, the product of x minus 1 squared has a starting at x minus 1 squared. The product of this with that starts at x minus, these are where the product starts. So these three things are only common, they become common, they'll become they all share common terms when we get to like the squared terms, right? The first one starts at the square, this one actually has one lower order term. This one has two lower order terms. So what I want to do, you're done? I guess you better. You're not done, but time is up. Yes. Thank you. Good. So what I'm trying to get at here, guys, is we should just split off. We should split off the zeroth order terms, which is there's a 1 from here. And then there is plus the first order terms. There is a is n equals 0 from here, which is there's 1 from here, and there's also 1 from here. So I think in total there's 3 times x minus 1, right? And then plus these things, all right, which I'll write again just to be annoying. All right. If I was smarter, I would do a little less writing, but oh well. Let's see here, plus the sum. I just peeled off the zeroth term, right? So now the middle one starts at 1. And I peeled off 2 of the terms on the last one. So the last one starts now at 2. All right. So what we want to do is reindex the first 2 so it looks like the last one, I think, is probably the nicest thing to do, right? So then we can add those 3 pieces together and have a proper answer. So this one we'll do, let's say, j equals to n plus 2. This one, we'll put j equals to n plus 1. This one, we'll just put j equals to n. All right? And so with those relabelings in mind, we get 1 plus 3 times x minus 1 plus the summation j equals 2 to infinity, parentheses. All right, so let's see here. That first one, what's n if j is if j is n plus 2, what is n? J minus 2, right? So this first piece gives me a 1 over j minus 2 factorial. Right? And how about the next one? Next one, n equals j minus 1 in the next sum, right? So that gives me a plus 2 over j minus 1 factorial, right? And then the last one, well, that's easier. That's just 1 over j factorial. All of that times x minus 1 to the n. And of course, the whole thing is all multiplied by that e to the 1 factor, which we split off earlier. There you go. Yeah. So the 3 to the x one is much the same thing. You got pesky natural log of 3 things muddying the waters, but it's the same. That's a template for what you got to do. Yeah. And then you could tack on like otherwise impossible questions to this. Calculate the 50th derivative of this function, right? Then you'd, oh, I'm sorry, I got an n here. That's crazy, right? That should be what? That is j, yeah. Right, anyway, next question. Let me move along here. I know our time is limited. What does that mean?
Problem.
Yes, you may assume that x is greater than 0, so you can use the alternating series test here, okay? Let's add that to the question so I don't get dragged into something I don't want to, right? So if x is positive, and you look at 1 over 1 plus x equals to what? 1 minus x plus x squared plus dot, 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 right? For x positive, this is an alternating series. So if I want, to have 1 over 1 plus x minus 1, parentheses, minus 1 minus x plus x squared plus dot, 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 plus minus 1, minus 1 to the n, x to the n, right? If I want this, the absolute value of that to be less than or equal to what? 0.01. So by alternating series estimation theorem, this is less than x to the n plus 1, right? So you want that to be less than 0.01, you said? I'm not sure. There must be more to the question. Oh, I told you you're just keeping the first two terms, right? So the question actually says you're just using 1 over 1 plus x equals to 1 minus x, right? And so that's good. So this is approximately up to what? Plus or minus x squared by the alternating series estimation theorem. See, because the first two terms in the binomial series are just this. The binomial series here is the geometric series. They overlap, right? Like 1 plus x to the minus 1 is binomial series. K equals minus 1, but it's also geometric, right? They're not mutually exclusive in that sense. So anyway, goodness gracious, all we got to do is x squared less than or equal to 0.01 and solve that inequality, right? So, yeah. Does that make sense? So the problem gave you that you're just using this to approximate the function, right? So if that's set in stone, the error is given by the next thing you haven't used, which in this case is x squared.
No, it makes sense. I was just thinking of it completely differently.
Oh.
So if x is negative,
That is true. If x is negative, it's still, I guess it's, oh, it's not alternating.
perhaps this is
If x is negative, then we have to look at Lagrange's form of the remainder, which I swore not to talk about today. So.
Doesn't it have to be 1 plus negative x for it to be binomial?
Does it have to be what? I mean, binomial, generically speaking, is something that's the result that 1 plus x to the power k, right, is 1 plus kx plus 1/2 k times k minus 1 x squared plus dot, 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 right? Which, in more detail, is the sum, n equals 0 to infinity, of k times k minus 1 times k minus 2, all the way down to k minus parentheses n minus 1, close parentheses, divided by n factorial, x to the power n. That is the binomial series that we derived from direct application of Taylor's theorem. It just so happens that this simplifies to the geometric series in the case that k equals minus 1. Kind of funny. See, minus 1 times minus 1 minus 1 times minus 1 minus 2 dot, 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 times minus 1 minus n minus 1, which is what? That's like minus 1 to the think it's minus 1 to the n, because I've got 1, 2, 3, da, 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 da. Well, that might be n minus 1 of them. How many is there? No, it's n. I think it's n, because this starts here, and yeah, I believe I have n factors here, since this in some sense starts at 0, so there's n products here. I'm starting by subtracting 0. I end at subtracting n minus 1. There's n products here, so that means that there's n minus 1s. And if you look at the numbers you got here, this is a minus 2, this is a minus 3, minus 4. What's this? This is n. Minus n, right? In other words, this is minus n times n factorial. So this simplifies to which is, of course, the geometric series. Yeah.
But,
In the case k equals minus 1.
what if you have one, this was the question I had, but if you have, what, k equals 1/3,
Oh, well then, it wouldn't be geometric, of course, but yeah.
but if you plug k equals 1/3 into the geometric series,
Oh,
I mean, not a binomial series, first thing that you get is 1, because it's supposed to go 1 plus kx plus k minus 1 squared over 2.
what are you talking about, Josh? I'm not.
Well, I'm talking about example 5 right now in the book, but
Okay.
it wasn't in some of the problems. And that kind of confused me a little bit because k equals 1/3 at x equals 0.
You mean
No.
this one?
At n equals 0. Yeah.
Where?
Page 669.
Okay, yeah. That is what I mean. This is another notation for the cube root of x. Yeah. So binomial series here, k equals 3, right? And so this is 1 plus 1/3 x plus 1/3 times 1/3 minus 1 x squared. I'm sorry, I'm missing a half there. So this should be actually, so that's 1/3. This would be 1/3, 1/2 times 1/3 times minus 2/3 actually, x squared. So that is 1 plus 1/3 x minus 1/9, I believe, x squared. So
Well, the first term is 1, and if you if you take k minus n plus 1, 1/3 minus 0 plus 1 doesn't equal 1 for the first term.
First term is always 1, isn't it?
yeah, you don't think it agrees with this? That's what you're saying? Doesn't agree with this? Was that your point?
If I place n at 0,
Yeah.
if I, give make k equal to 1/3, then how does that equal 1?
Let's see here. So if you want to think about you want to think about the case n equals to 0, right?
Yeah.
Okay. Because you don't see how that produces the 1. The question is, what does this numerator mean when n equals 0, right? Yeah, I think that the answer to your question is not going to be very satisfying because basically it's our convention for this symbol to mean 1 in the case n equals 0.
So that's only valid after, at and after the second derivative of the function. Because then it starts equaling k times k minus 1,
Yeah.
k times k minus 1, k.
I mean, we could always fall back on the derivation, right? I mean, this was a summary of a pattern that we derived. So the function we had was 1 plus x, in this case, to the third power, right? Or more generally, to the k power. So this is equal to f of 0, right? Plus f prime of 0 times x, and so forth and so on. So this is the 0th term. The 0th term is 1. Because f of 0 is 1. And f prime of 0 is k.
I understand that. I guess what had me confused was that if I place n equals 0 as a student.
So this is why I write the general formula, and I also write the first few terms so that there's no ambiguity about what n equals 0 means. Who knows?
So for the series, then would it be better to say that that's true for n equals 2 to infinity?
Well, I mean, if you want to, I guess you can, if it's bothersome, you can write 1 plus x to the k equals to 1 plus the sum n equals 1 to infinity of k times k minus 1 times k minus n minus 1, right? But I don't think it's needed.
I'm sorry. It's just been annoying me.
Okay.
Yeah.
Take a look. Oh, sorry. Just like how it looks on the picture. Oh. It should be
I mean, whenever you write something like this, it's it's trying to communicate a pattern. And we should go on. Yeah. It's okay. Questions?
I'm saving my Diffie Q for office hours tomorrow.
Uh-oh.
About 272. Problem 272. Right here. On this one.
Yeah. There's two ways to go down the road. Go here. Here, I'll do one like it, but not this one exactly. That one. Yeah. So this is I don't know. I ask stuff like this on a test a lot of times, and then it confuses students, which is unfortunate because this is probably this might be the easiest problem in the homework. I mean, it might be. Maybe. I'm not sure. It depends on how you go at it, though. So suppose we had f of x equal, I'll just use x cubed, plus x squared minus 2. And you want to find power series for f of x centered at x naught equals to, I don't know, 3, whatever. So there's two kind of, oh well. Anyway, so there's two approaches here. The first approach, which I would not advise for this one, because it's just awful. So you could go, oh, that's x minus 3 plus 3. I can cube that, and then I do x minus 3 plus 3. I square that, and I subtract 2, and you just do algebra. And that will produce the power series centered at 3. If you just keep these together, you know. This is a bad way. Approach number 2 is to use Taylor's theorem, which says that f of x is f of 3 plus f prime of 3 times x minus 3 plus 1/2 f prime prime of 3 times x minus 3 squared plus 1 over 3 factorial f prime 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 of 3 times x minus 3 cubed. Close enough. Let's see here. Now this is obviously the way to go because, you know, we can take derivatives of polynomials and evaluate them at 3 all day long and we wouldn't break a sweat, right? I mean, that would be, if someone would pay us money to do this, we'd be like, sure, please. It's a job I'd like to take. Well, maybe not. It would be boring, right? But, so, all right. So my advice would be to actually make a list. Here we go. F of x equals to, so I advise a tabular presentation of your work here to keep you straight. So what I do is I write the derivatives on a stack of them here. Write the derivatives here, and then I'm going to write the values at the point. Of course, so the Taylor series, in principle, has plus dot dot dot, right? But in practice, everything in the plus dot 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 is identically 0 here. All right, so set x equal to 3. What do you get? F of 3 is 27 plus 9, 36, 36 minus 2, 34. F prime of 3 is what? 3 times 9 plus 6, 33. Because 3 times 9 is 27. 27 plus 6 is 33. F prime prime, that would be 3 times 6, 18 plus 2, 20. F prime 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 of 3 would be, oh, that one's easier, right? This is a great contrast to uglier functions, right? Uglier functions, when we find the Taylor series, the further we go up, the worse it gets, right? With the polynomials, it's exactly opposite. So anyway, take all of this, and you can write down the answer. 34, if you understand your Taylor's theorem, that is. 33 times x minus 3 plus 10 times x minus 3 squared plus x minus 3 cubed. There it is. Now, the fact that the top coefficient was 1 is completely unsurprising if you think about cubing this, where the cubic term comes from. It comes from this multiplied by itself 3 times, right? So that's got a coefficient of 1. The fact that like the highest power has a coefficient of 1, totally unsurprising here. And also the fact that we've got a 34 is also unsurprising if you start looking at it, because you're going to get minus 2 from here, you get a 9 from here, you get a 27 from that, which is exactly what we calculated, right? 27 plus 9 plus 2. Minus 2, rather. So if you understand this, problem, what was it? 272-ish. So you should be able to do 272 with ease now. Yeah.
Yeah, I just looked at it, got scared.
Understandable. Let's look at number 20 from section 9.10. Supposed to find the binomial series, at least part of it. I'll find the first three terms of 1 over the square root of 1 minus x squared. So let me convert this to a unabashed binomial series problem. This is 1 plus u to the minus 1/2 power with u equals to what? U is minus x squared, right? Now, I've got the right pattern. I can write down the binomial series. First three terms with minus 1/2. That would be 1 minus 1/2 u plus 1/2 of minus 1/2 minus 3/2 u squared, and then plus stuff. So it's always ku plus 1/2 k times k minus 1. Those are the first three terms there. Now I can undo my substitution. What do I got? 1 plus 1/2 x squared, right? Plus 3/8 x to the 4th. And there you go. Those are the first three terms in the Maclaurin expansion for that function. Yeah.
If we're asked to find the complete power series for a binomial series where k is not a positive integer, can we use k choose n notation in our sigma notation? Write k
Well, I mean, I would probably think this is, yeah, it's probably not standard here to do that. The complete answer would have been some, right? N equals 0 to infinity of 1/2 times, 1/2 minus 1, minus 1/2 rather, minus 1/2 minus 1, dot, 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 minus 1/2 minus parentheses n minus 1, divided by n factorial, right? And then, well, what would go here would be u to the n, right? U to the n is equal to minus 1 to the n, x to the 2n. So let me just write that down here to save myself some writing. Minus 1 to the n, x to the 2n. There would be the honest to goodness complete answer. But, actually, if you look at that, that's easier. It's actually, in some sense, easier to write that than to write the first three terms. If I ask you to find the first four terms, it's definitely easier to write the complete thing. Because you actually have to figure out these numbers, right? The 1/2, the 3/8, Whereas this is, this is something that we can use to produce those numbers, except at the 0 case. I think n equals 1, it makes sense. Because if n equals 1, it means that this isn't present. If n equals 1, then I would say it's just the first term.
Oh, yeah.
Yeah.
Oh, wait, if n equals 1, then the first term would be minus 1 over 4. I mean, 1 over 4.
Let's agree to disagree. So this much we should agree on. These are the first two terms. So, and it is popularly agreed upon that this expression produces that as well. But I understand if you don't see it that way, it's fine. Definitely when we get to 2, there's no consternation, right? I mean, okay. It's okay. It's okay. If I was more awake today, I might be able to argue with you, but I'm just not there at the moment. There may or may not be a defense against what you're complaining about. You are free to complain. I invite these kinds of complaints. These are welcome. Indeed, the absence of these complaints makes me think that no one's actually paying any attention at all, and then that's much sadder. So, yeah. But not without precedent. Let's see here. Other questions? Before I make up other ones?
Could you do the sample
Yeah, we can go back. So back,
Let's do an abstract one.
way back. Section 9.7, right? Or was it 9.6? I can't remember. Oh, maybe?
9.7.
Yeah, okay.
Oh, no, 9.8.
Oh, you're right. You're right. Thank you.
With the integrals before you do that, with the integrals, do you turn
Intervals, you mean?
integral into a series before you take the integral of it?
Oh, you're talking about integrating using power. Are we talking about interval of convergence, or are we talking about using power series to integrate?
I brought both up. Let's do IOC first.
IOC first. All right. Let's see here. Let's see here. We could look at like number 72 and 9.8. That's not too awful. Oh, actually, that has a different. Stink. That actually has fine print I don't really care to talk about at the moment. Let's see here. I could try number 37. Here we have the sum n equals 0 to infinity, right, of x over k to the n. K is positive. I wasn't trying to find a weird one. Oh, man. I have the worst luck. Did we already talk about this? I know we talked about one of these. I don't know if this is the one I talked about already.
I think it was 36 we talked about before.
Oh, okay. So this probably is not bad. So we're supposed to find the interval of convergence, I think, is what it boils down to. Yeah. So what we do is we consider ratio test, right? Think about the ratio test. And to do that, I would look at x over k to the n plus 1 divided by x over k to the n. Now that simplifies, of course, and I'm supposed to take the absolute value of that, right? Right. So that simplifies to the absolute value of x, right, times what? You got k to the n divided by k to the n plus 1, am I right? K is positive, so it sneaks out of the absolute value unnoticed. And, well, great, that's the absolute value of x divided by k. We need this to be less than 1. So apparently, the condition on x is that x is less than k. So this tells me minus k to k is a subset of the interval of convergence. So from minus k to k, not included, is definitely points of convergence for this series, this power series. Now, we have to check the endpoints, right? So we put x equals to k. That's one endpoint, right? And what's that do for us? That gives us the sum, n equals 0 to infinity, of 1. Yeah, right? K over k? Fine, I'll write it down. K over k. Is that okay? Let's see here, sorry. This is going to happen at least once per lecture in this chapter. Let's see here. So that's 1 to the n. On the other hand, if we look at x equals minus k, we get some. So this is considerably easier than the one that Nathaniel ambushed me with the other day. Let's see here, k over k. Like this one is a friendly test question as opposed to the one that we talked about the other day. that had the end of the n or whatever. It was awful, but both of these diverge, right? Why? Right. Because the nth term is 1. Just plain, I don't even need the n here, right? 1 to the n is 1. 1 definitely doesn't go to 0 as n goes to infinity, okay? And minus 1 to the n does not go to 0 either. It doesn't even converge to anything. It oscillates at infinity. So both endpoints diverge, and therefore, we get to conclude that the interval of convergence here is actually equal to minus k to k, both of them not included. Ratio test always tells you the open interval which fits inside the interval of convergence, if there is one, and past that we have to check endpoints. The caveat to that, of course, is that if we there's some which just have the center of the series as the only point of convergence, right? And that pretty much means that the ratio test fails except when x is equal to the center, right? I mean, technically a singleton's not an open set, so I really shouldn't say that. Anyway, I'm going to shut up and I'm just talking about things that don't matter. Well, tomorrow is another day. Good luck.